Good evening, everyone. My name is Christopher Johnson. I'm a PhD student at UC Berkeley, and I want to talk to you about some of the research I've been doing there and some of the ideas and perspectives that I have on how we can continue to make progress in geodesy. So, as everyone in this room knows, geodesy is the science of measuring the planet, and more specifically for the application side of it that most of us do is the differential movements that we are interested in for a very specific problem. And there's been a lot of advances made over the years. So I got into geodesy about 6 years ago. During my bachelor's degree, I was involved with a GPS campaign in the Eastern California shear zone. And what I ended up doing is learning a lot about diffuse deformation along an active plate boundary, but more importantly, I learned that the connection between earth science and geodesy is really critical to understanding a lot of these complex problems. So the research that I focus on now is really central to problems in active tectonics. And I use both geodesy and seismology to look at a lot of different problems. So what I really focus on is the transient loading and earthquake triggering from that so that we can start learning more about fault properties. And this requires a variety of tools. So from modern seismic networks and continuous GPS and INSAR, we have a pretty good understanding of the large-scale loading rates on faults. So what I'm really focusing on is these transient loads that we're able to detect now as we get this higher spatial and temporal resolution from these really great data sets that are coming online every day as the advances are made. And what we're able to do with this is really start looking closer at a lot of new problems that have been around and looked at with older tools, but what we can use is these really dense data sets to start combining the application to these modern problems. So one of the big things I look at is earthquake triggering, and one of the problems with that is when you just use the seismic data, you typically need something with geodetic resolution so that you can see if there's aseismic deformation. But you don't have that in a lot of areas. But for other problems, such as surface loading, we can start using the continuous GPS network, and what we're able to see now is that the response from the hydrological loading is a really strong signal. And what we can do with that is start looking at the long-term surface deformations and start looking at how the stress evolves through time, and then tie that back into the seismicity that we're seeing. And what we're really doing is start to learn a lot about the faults and how they respond to these different annual stress changes. And it's really pushing the envelope on what we can see with these different tools that we have available now from all this streaming data that's coming online. And more importantly, it's giving us a better estimate of the stresses that we can see. So moving forward with this, what we really need to do is continue to maintain these networks. So the GPS has been in place now, and there's a lot of work that can still be done with the data that's already sitting there and what's still coming online. Start looking for new transients, and the noise is one thing. But additionally, we can start to reoccupy some old benchmarks. They're everywhere, and they can really point us in a direction where we might want to start looking for other sources of deformation, specifically with INSAR. So as these new satellites come online, we can get more and more data coming in and start stacking these things together. But one of the big problems that we still need to keep working on with INSAR is the atmosphere correction. So there's current work already being done with models and dual frequencies, but another thing that we can do to really push this forward is involve the atmospheric community so that we can start to interpret that data instead of just consider it noise and throw it away. But combining all this together with seismology is already being done. So the co-location of the GPS systems that are in place with seismometers and accelerometers is really pushing the envelopes for what we can do with early detection and also getting a better understanding of ground motion. But we can also start using the seismic and geodetic methods for other things like the early warning. So coming online now, you have the ability to turn your smartphone into a seismometer, and we're hearing these things can also be possible with the GPS in your smartphone. So my takeaway point is that integrating all these data sets that we have at our disposal now is really key to moving forward, and we can really make more and more advances in the fault mechanics and characterizing the structure of these faults, and hopefully get to where we have more and more INSAR data coming in online and we can improve the hazard assessments. A lot of the work that I do now wouldn't be possible without the data that's coming in, streaming right now, and it'd be great to see those same improvements in the next 20 years. Thank you.